Swayam Prabha. Digital India. Educated India.
Okay, so with the basic understandings of what is rheology and whether it is applicable to our earth systems or not, now we are in this slide to classify the different types of rheologies that we commonly see in all materials and also within the rocks. So, we can have three different kinds of rheologies. One is elastic rheology, then the second one is viscous rheology, and the third one is plastic rheology. With the course of time, we will see that elastic rheology, when a material is deforming under elastic manner, the strain or deformation is recoverable, and when they are deforming following viscous or plastic manners, they are non-recoverable. Now, I would like to remind you one very important thing that we commonly mistake in describing structural geological deformation features. And with these three rheological terms, elastic, viscous and plastic, we sometimes use more or less similarly the two terms brittle, ductile, and sometimes brittle ductile. Now, it is very important to remember that the classification of rheology has nothing to do with the brittle and ductile deformation. Now, brittle and ductile deformation only considers whether the cohesion of the materials are maintained or not during the deformation. That is it. It does not consider the rheological part. If the cohesion is maintained, then it is ductile. If the cohesion is not maintained, then it is brittle. Now, you can say very generally, but that is not strictly true for all cases, that brittle deformation is most of the time plastic, and ductile deformations mostly include everything which are not elastic and not brittle. But remember, brittle and ductile, these two terms have nothing to do with elastic, viscous and plastic rheology. So, we will now slowly describe the concepts of what is elastic, what is viscous and what is plastic. I will mostly show you the classic considerations of these three rheological terms, their analog visualizations, that what is the best way to represent this rheology with some known materials we have, and then we will derive some sort of different material constants or rheological constants, and we will see their implications also in the study of structural geology. So, let us start with the elastic rheology. Now, the definition of elastic rheology is given by the Hooke's law, and it says that stress is linearly proportional to strain and the latter is fully recoverable. As I said in the previous slide, that elastic rheology, in elastic rheology you can recover the strain, and the elastic rheology is best visualized by a spring, or in other ways you can have any elastic band or rubber band, and then if you stretch it, it expands, and if you release it, it comes back to its original position. But if you stretch it more, it does not come back to its original position, but that is something different. So, let us see what we can take out of it. So, what we have this particular group of images here. This is written T1. At T1 we have one spring, it has a finite length, and then at T2 I have added one little load here with this green bar. because I have added this little load on the spring, you can understand if spring is hanging, I added a load at the end, so spring would expand, and therefore the length has changed. If I add more load, the spring would further expand and change the length, and so on. Now, if I start releasing the loads or taking off these green bars one after another, the first one, after the first one, it would come back to the load very similar. It showed the expression with the 2 green bars. If I take one more out, then I have only one, then it would come back to the load that we had, or to the shape or to the length that we had with the 1 bar at the beginning. And if we remove all these loads, then it would come back to its original position and original shape. So, if I now plot them in displacement versus force curve, then with the application of force, the 3 different loads I have, when we are loading it, then we can get some points, and if I connect these points, they generally fall in a linear pattern. And when I release these loads, that means this side, they also fall, they come back in a very similar fashion and also maintain a linear relationship. We can also visualize this image in a different plot, what is given here. In one plot we have stress versus time, in another plot we have strain versus time. This strain you can visualize in terms of elongations. So, till this point it was T1, where we did not have any load, any stress, and the strain was also 0. Now, then we slowly started applying the load with this green bars, and we see the strain also, or elongation also, increased. Now, if we leave it with the 3 green bars here for quite some time, the strain would remain constant, and if we release the load by removing the green bars, then it would come back to its original position. So, what we see that this stress versus strain in this diagram has a linear relationship. So, stress is proportional to strain, and the linearity constant is defined by E, which is Young's modulus or the elastic modulus, or sometimes it is known as stiffness of a material. Now, in some books or texts you may find that E is written in people are writing E as Y. So, you just have to see what is their common understanding. The Young's modulus is defined as the slope of the stress strain curve. We will see it later. So, this is also known as, this equation is also known as Hooke's law, and it is a constitutive equation because we have dynamic parameter in one side, kinematic parameter on one side, and they are related by a constant. So, physically E is quantified how hard a rock is to deform elastically, and that is why this term stiffness came in the picture. Now, to talk more about elastic rheology, as we have seen, or we have understand that elasticity is time independent. That means, does not matter how long you keep the green bars, it would stay at its position, and then you remove the green weights or green bars, it would come back to its original position. It is not a function of the time. Therefore, the ideal elastic material would come back to its original position irrespective to the time of the stress it is being applied within the elastic limit. And of course, the rate of stress application would increase the rate of deformation linearly. Now, if I add more green weights or green bars and I do it quickly, then the elongation of the spring would happen also very quickly. So, if I would like to see, then stress versus strain, it is a linear curve. This is what the relationship we got. So, sigma equal to E multiplied by strain. So, therefore, the slope is your E or Young's modulus. And then if I increase the stress rate, that means if I increase the loading rate, then strain rate would also increase linearly. So, we can write sigma dot, which is actually sigma by T equal to Young's modulus epsilon by T, or you can write it epsilon dot. So, this is again the Hooke's law. Young's modulus therefore is the ratio. If I can come here from this equation, we can get here that it is the ratio of stress versus strain along the same direction. That is important, that you cannot measure stress in one direction and measuring strain in other direction. You divide them, you get a ratio and you say this is my Young's modulus. That is wrong. You have to measure them in the along the same direction. Now, you can replace this Young's modulus by another constant, which is called shear modulus. So, if you shear this elastic material instead of extending it, then this is known as mu, and sometimes it is also expressed as G. So, you can equate Young's modulus equal to 2 of shear modulus or twice of shear modulus, and then this equation takes the shape, the Hooke's equation or Hooke's law takes the shape of tau equal to 2 mu gamma, where tau is your shear stress, mu as we have explained, this is shear modulus, and gamma is your shear strain. Now, so from these we have already found two constants, one is Young's modulus and another is shear modulus. However, from the Hooke's law we can also get 3 other elastic constants. So, one is Poisson's ratio, another is bulk modulus, and the third one is Lemmy's constant. In fact, in some textbooks this mu and lambda, this mu and these two terms, they are together referred as Lemmy's constant. Poisson's ratio is generally referred by Greek letter nu, and bulk modulus is generally referred by Greek letter kappa. Let us see what is Poisson's ratio. Now, we have talked about volume constant deformation and so on. So, if I have increased the length of the spring in the previous example, then if this volume of the spring I have to keep it constant, then it has to shorten in some other directions to keep the volume of the spring constant. Now, this is the example, this little drawing. So, what we are visualizing, it is on x z plane and y is perpendicular to our to the board or parallel to our view direction. So, this was initially the width of this bar, say this is a spring and this is the length of this spring. Now, upon applying this load, these green bars, then I can figure out the strain which is along x direction, which is epsilon x, and if I consider this is cylindrical and a perfectly isotropic body, then on this direction it has to shorten to keep the volume constant, and therefore, epsilon z and epsilon y should be equal. So, this is only possible if the material that we are considering, the rock we are considering, is isotropic. The shortening therefore, will be the same in any direction perpendicular to the elongation direction, and if the volume is preserved, then the elongation along x axis should be balanced by the shortening along y and z axis, and therefore, you maintain your volume. So, we can write therefore this equation that E x, that means the elongation you happened along x direction, should be equal to the sum of E y and E z. Now, these are happening in different directions. So, therefore, I have a negative sign. Now, E y and E z, because this is an isotropic material, they are equal. So, I can write them minus 2 Ez, or I can also write it as minus 2 Ey. Whatever be the case, Ez or Ey, we can now further summarize this equation as Ex multiplied by 0.5, because these 2 can come to this side, equal to minus epsilon z. This minus sign further signifies that if you extend along x direction, you have to shorten along the z direction, and then it is related by a numerical value 0.5, and 0.5 you can consider that it happens when the volume is remaining constant. So, this relationship 0.5 epsilon x equal to minus epsilon z, this tells us that elongation in one direction is perfectly balanced by shortening in the plane perpendicular to the elongation direction, and when that happens, then we call it perfectly incompressible material. That is, the materials that do not change their volume during deformation. So, therefore, if you have your volume constant, that 0.5 value is therefore maximum, right. So, most of the rocks we know, or we will see later, that they are not perfectly incompressible. All sorts of volume changes or compressibilities are involved where the volume shrinks. Okay. So, to account this changing volume or compressible volume of the rock mass that we are considering, instead of writing at 0.5, people do replace it with a constant, which is constant for a particular material, and this constant is known as Poisson's ratio and represented by this Greek letter nu. And as you can see, Poisson's ratio must be a dimensionless quantity, because it is a ratio of the two strain parameters. Okay. So, Poisson's ratio essentially characterizes the compressibility of a rock perpendicular to the applied stress. Now, I give you a very simple example of Poisson's ratio that we use, that you may have seen some glass bottles where instead of the caps we use to seal the glass bottles using some corks. Now, the corks are very interesting material in the sense that, because if you have the bottle and then you have to press the cork inside, because you are pressing, and if the cork has to maintain its volume constant, so you are compressing it this side, so length is shortening on your compression direction, so it has to expand on the other direction. That means the cork is now expanding and it cannot go inside the bottle's mouth. But cork is such a material that this expansion is very less, and therefore, we use sometimes to seal the mouth of a bottle using a cork. There are some other materials that do have some sort of negative Poisson's ratio. That means, if I compress in this side, instead of expanding in this side, they can also shrink, or if I extend something in this side, instead of compressing in this side, they actually extend. These are some complex composite materials. Honeycomb is one of the examples that you can think of that do have negative Poisson's ratio. So, most of the rocks that we generally consider in the wide range of conditions, they do have Poisson's ratio between 0.2 to 0.33. It is not a very wide range, but in terms of Poisson's ratio, it is pretty wide. Now, 0 or negative Poisson's ratio, as I talked about, is also possible for a few special materials like foam and honeycomb, but extremely rare for rocks and minerals. With negative Poisson's ratio for a common isotropic rocks or minerals we do not see, but people have reported some sort of negative, very little negative Poisson's ratio in some particular directions of some anisotropic minerals. So, you can also express the Poisson's ratio in terms of the velocities of P waves now and S waves. Now, this is something little difficult to understand right at this point. But if I say you that these seismic velocities that we consider, these P waves and S waves, these are elastic waves, and we are dealing with elastic rheology. So, there must be some sort of relationships. So, what is P wave? P wave is when the particles do oscillate in the direction of wave propagation, and S wave is some sort of body waves where the particles oscillate perpendicular to the propagation direction. So, you can see that these two terms are very important, that one is propagating along the propagation direction or oscillating, not propagating, one is oscillating along the propagation direction and another is oscillating perpendicular to the propagation direction. So, is not it very similar the way we can think that if we compress this side and the things would be extended. So, one is perpendicular and one is parallel. So, their relationship if we write, then Poisson's ratio in a different way can come in this form, and this is very useful because in deep earth we only receive the signatures we get from the deep earth, except some rare cases, mostly the seismic waves. And with the analysis of the seismic waves, it is possible to determine the Poisson's ratio of the deep earth rocks, and also this is important for the hydrocarbon industries, because this gives us an estimation of fluid properties in the hydrocarbon reservoir. So, for example, you can think that if the Poisson's ratio, if the Vs is 0, that means there is a fluid, and then Poisson's ratio must be close to 0.5 and so on. Now, so we have learnt now 3 elastic constants, one is Young's modulus, one is shear modulus, we just learnt Poisson's ratio. Now, let us talk about the bulk modulus. The bulk modulus or kappa is the inverse of the compressibility of the medium. So, in general it measures the relative volume change of a fluid or solid as a response to a pressure of mean stress change. Now, we have learnt what is mean stress in our stress lecture. So, volume change is defined by this del V versus V0, del V is del V1 minus V1 minus V0, where V1 is your changed volume. I just write it because I think I confused by my statements. So, V1 minus V0 by V0. So, this you can write del V by V0. That is your relative volume change of the material you are considering with the change of the pressure. So, if I am increasing the pressure or decreasing the pressure, how much volume change I am experiencing or the rock is experiencing within the elastic domain. So, that is your kappa or bulk modulus. So, this is you can write it this way. So, this is your pressure change and this is your volume change, and then with some calculations and relationships you can figure out that you can express your kappa in terms of shear modulus, Poisson's ratio and Young's modulus and Poisson's ratio. And this equation says that you need more pressure to compress a rock when the value of the bulk modulus goes high. Now, we have now learnt Young's modulus, we have learnt shear modulus, we have learnt Poisson's ratio, and we have learnt bulk modulus. Now, there is also one left, Lamy's constant. We will learn it later, but not right now. But I would like to give you at this point few considerations. So, all elastic constants are related to each other, because you are measuring it from a same material. So, they have to be related to each other. So, you need out of these 5, you need only 2. If you have only 2, then you can calculate all 3 other elastic constants. And this is most important, all elastic constants are direction dependent. So, when you say Young's modulus, you measure it in a particular direction, Poisson's ratio you measure elongation in a particular direction and then shortening in a particular direction and so on. So, if these are direction dependent, therefore, a single anisotropic rock or mineral should have more than Young's modulus, one more than one Poisson's ratio, and so on. Or what I mean by that, if I have a rock in 2 dimension, if I draw it like this, so the dotted areas are 2 different materials. Now, if I deform it, extend it in this direction, then the Young's modulus I would get along this direction. Okay. But if I extend it along this direction, the Young's modulus I would get is along this direction. Now, because this is anisotropic, we have 2 different materials. So, if I consider this one as E1 and this one as E2, this is also a measure of anisotropy, elastic anisotropy in terms of Young's modulus of this rock. Now, the generalized Hooke's law is something is little expanded from what we have learned. This E equal to Young's modulus multiplied by strain, and but this equation is typical, and you can see that it does not include any direction that we talked about, it does not include the anisotropic components. So, therefore, the generalized Hooke's law is written in this form, in this tensorial form. We know more or less what is tensor. So, sigma ij equal to C ij k L epsilon k L. Now, sigma ij for 3 dimension I equal to 3, j equal to 3. So, you can have 9 components here and so on, and for 2 dimension you can have then I equal to 2 and j equal to 2, then you would have 4 components there. So, sigma ij here is the total stress tensor, epsilon k L is the strain tensor. Now, this term C I j k L, this term describes the all elastic constants in one house. This is a matrix. So, this is stored in one matrix, and this is known as stiffness matrix. Now, this stiffness matrix you can represent it by 81 coefficients, simply because you have 9 components here, you have 9 components here. So, this matrix has to have 81 components, but we know that sigma ij and epsilon ij are symmetric tensors, and each of them can then only have 6 components. So, therefore, this 81 coefficients of C I j k L or the stiffness matrix reduces to number 36. Now, you can further reduce it by using some strain energy relations, then it comes to only 21 independent coefficients. Now, if this equation is written this form, that sigma I j equal to C I j k L strain k L, you can also express in terms of strain. So, instead of that you can write strain I j equal to, I am sorry, then it will be a different matrix S I j k L stress k L. Now, C is known as stiffness matrix, and here S is known as compliance matrix. So, this is something that you may note. Now, these expressions, that how there were 81 coefficients and then out of that we get 36, and then using strain energy we can get 21 independent coefficients. You may not have to go to the detailed derivations of this, but at this stage it is important that you know that from number 81 you can come down or you can reduce the independent coefficients to number 21. Now, let us treat this equation in a different way. And if I have to consider this as isotropic material, then this generalized Hooke's law you can express it in this form, okay, where sigma I j equal to lambda, which is one of our Lami's constants, then sigma k k Kronecker delta del I j plus 2 mu epsilon I j. Now, Kronecker delta is a very interesting term. If I equal to j, then it becomes 1. If I not equal to j, then it becomes 0. So, for shear components, therefore, if I have applying a shear modulus, that means I not equal to j, therefore, if I consider I equal to 1 and j equal to 2, whether they are not equal, then we can write sigma 1 2 equal to 2 mu sigma 1 2, because then Kronecker delta I not equal to j becomes 0. So, this term vanishes, and here we get mu as the shear modulus. So, you can see how from generalized Hooke's law we can derive the shear modulus, just implying or just taking into account the shear components of the matrix. And if it is for normal components, that means I equal to j. So, therefore, Kronecker delta value should be 1, and this can be expressed with some geometric with some algebraic calculations. You can represent it further by this, and therefore, you get the bulk modulus from this equation. Now, this is how it is done. This slide, what I would recommend you, that you do not have to go into the all details of this equation and how it is derived, but it is important that from the stress tensor, when we apply this to this elastic field, we know that it has some normal components and it has some shear components. So, when we apply the normal components, we get the bulk modulus related to volume change and things like that. You remember that mean stress and all other issues. And when we are not dealing with the normal components, that means off diagonal components where your shear stresses are acting, then you can get simply by considering I not equal to j, you can get the shear modulus of the elastic material. Now, with this I would stop, and then we will move to the next topic, viscous rheology.